Alright, in this video we're going to be working the CalBC Unit 1 quizzes, the Form I's and Form J's. So the first one, quiz 1.1, this is about the definition of the limit. We're going to look at the graph of y equals f of x. What's the value of the limit as x approaches 1 from the positive side? Okay, so we're thinking we're going right there. The closer that x gets to 1 from the right, the closer y gets to 2. So I'm going to say that the limit as x approaches 1 from the positive side of f of x equals 2. Does the limit of g as x approaches 2 exist or not exist? I'll explain my reasoning. I'm going to say it does exist because, all we have is a removable discontinuity, now that we know what we know. I'm saying, okay, here we have the best response would be yes, because both one-sided limits are both existing and agreeing. So I'm going to say the limit as x approaches 2 from the left is equal to 4, which is also equal to the limit as x approaches 2 from the right. Okay, and when we were grading this, you didn't have to have this, but this was definitely the best response. Okay. You had to have something indicating that it was going to the same y coordinate as you approached x equals 2 from both sides, but it didn't necessarily have to be that. But, this is something to aspire to. Graph of y equals h of x shown here. What's the value of h of 1? H of 1 is going to be where the filled in circle is. That's going to be 1. All right. 4. The limit as x approaches 1 of 1 plus e to the x over 2x squared. Well, we should always try to just plug in a limit. I think this one's going to work out fine. Okay, this is going to go to 1 plus e to the first power divided by 2 times 1 to the second power. That's a number. That's a safe place for us to stop. We're going to stop there and move on. Okay. We're going to consider the limit as x approaches 2 of fx. So we're going to need to consider both one-sided limits. Okay, as x approaches 2 from the left, that's where it's more negative than 2. That's going to be 2 times 2 plus 3, which is 7. And then as we approach from the positive side, that's going to be 2 squared plus 1, and that is equal to 5. And since these aren't the same, the limit from the left is not equal to the limit from the right, I'm going to say the limit as x approaches 2 of f of x doesn't exist, okay, because of that. Okay, and it didn't say really to explain my reasoning or anything here, so I think that'll be enough. That's fully justified. So g is defined below. What's the limit as x approaches 1 from the negative side of g of x? Okay, well, so we're just really interested in where x is less than 1. The limit as x approaches 1 from the negative side of g of x is going to equal 1 minus 2, which, okay, I can need that. That's negative 1. Okay. Then down here, the value of the limit as x approaches 5 of x plus 5 over x minus 5. Keep in mind what we knew at this point. We didn't really have the tools to deal with infinity. So we said if it was going to 10 over 0 or something like that, we said that didn't exist. I still think, even knowing what we know, this wouldn't exist because this would be, it would be going to positive infinity on one side and negative infinity on the other. So I would say that limit fails to exist. Okay, and that's Form I. Move on. We'll do Form J. It's going to be very similar. Here we're looking at the limit of h of x as x approaches 3 from the negative side. So I'm going to be, okay, x is approaching 3 along the graph of h from below, and y is getting closer to 4. So I'll say that the limit as x approaches 3 from the negative side of h of x is equal to 4. That's the y coordinate. And then now we're going to ask, does the limit as x approaches negative 1 of g of x exist or not exist? Okay, we see that we've got some sort of jump, but it is filled in here, so it's like, what's going on? I would say that the limit as x approaches negative 1 from the left of g, well, that's going to equal 1. can see from the graph, we're getting closer to 1, while the limit as x approaches -1 from the positive side, okay, over here, that's staying pretty constant at 2. Looks like it's 2. And it's clearly not 1, right? It's not going to the same spot. So I say that the limit doesn't exist because, you know, these aren't the same. I'm running out of room here, but I can fit that. Limit of g as x approaches -1 from the positive side. Okay, that's very well explained reasoning. All right, now we're going to look at the graph of y equals f of x. What's the value of f of 4? Okay, it's where the filled-in circle is, and that's looking like it's happening at 3. So I would say f of 4 is equal to 3. Okay, we're going to... All right, find the value of the limit as x approaches 1 of x plus e to the x over 2x squared. Oh, this is the one that's the same on form I. I forgot to change it. Didn't need to be changed a whole lot. We're just going to plug in 1. This is just a number, and it's not division by 0, so we're going to stop there, right? That's just some number. Definitely not a rational number. What is the value of the limit as x approaches 2 of f of x? All right, well, I'm going to have to consider the one-sided limits. Okay, so as x approaches 2 from below, where x is less than 2, I'm going to say, all right, this is the limit as x approaches 2 from the negative side. That's going to equal 2 times 2 plus 3. Is this exactly the same as the other form? Oh, that's a shame. That wasn't supposed to happen. I think I had intended for, on this form, for this limit to not exist, and then this one to exist, but whatever. What's happening here? It's a shame. So this is equal to 7. You know, if I think I had intended to make that x squared plus 3, maybe. Yeah. And then it would have been 7 and 7. And then I would have said, yes, the limit does exist. But if you just, you know, went straight to form J, then you'll see, okay, as I approach 2 from the positive side, I'm going to be taking 2, squaring it, adding 1, only getting 5, and since 7 and 5 aren't the same, right, I'm not getting the same thing from each side. And all right, so g is this function, and we're going to ask what's the limit as x approaches 1 from the negative side. Yeah, I'd intended to ask what's the limit as x approaches 1 from the positive side, but, you know, I think it's dry. So I think I'll do limit as x approaches 1 from the positive side, because I'll probably have fixed this quiz by, you know, next year. And so this would be limit as x approaches 1 from the negative side of g is going to be 1 minus 2, which is -1. But had I asked what I intended to ask, which is as x approaches 1 from the positive side on this form, that would be 1 plus 2, which, as you know, is 3. Okay. And then this one, I think I'd intended for it to be division by 0 anyway, so if you're looking at a different problem that's non-zero divided by 0, then it's going to be the same result. Okay, when I plug in 5, this one's going to go to 10, that one's going to go to 0. 0 in the denominator is bad news. Non-zero in the numerator is even worse news. There's nothing we're ever going to be able to do about this. This is going to be one of the infinities, or DNE. At this point, you didn't really know, right? If you think about quiz 1.1, you hadn't learned about infinities yet. So we're going to say the limit as x approaches 5 of x plus 5 over x minus 5 just doesn't exist. And that's all for 1.1. All right, quiz 1.2, this is the one about the limits involving infinity. And this was the one that it seemed like in my class people struggle with the most in this unit. So I'm going to go real slowly through these. We're going to start by finding the value of the limit. X to the 4 divided by e to the 4x. Okay. In our taxonomy of growth rates, the fastest growing is exponential. Okay. So exponential is growing faster in the denominator, dividing by more, getting closer to 0. Okay. Faster on the bottom, as x goes to infinity, that's going to 0. just provided that where you don't have like e to the negative 4x, because then that would be like having e to the 4x in the numerator. I don't know that we've run into that situation, but that's one that we need to be aware of. Anyway. Okay, this one, x approaches infinity, so I'm thinking about growth rates. I've got 3 powers of x in the numerator, 3 powers of x in the denominator, so I know that since the exponents are the same, I'm going to be dividing coefficients. So it's going to be 2 divided by 5. F is a continuous function with domain x bigger than 1, and f is always positive in its domain, and that graph has asymptotes x equals 1 and y equals 5. Okay, I'm going to try to draw a little picture for you. Okay, this is going to just be x equals 1. Maybe I'll just say x equals 1 right there. There's that vertical line. And then I'm going to kind of come across with y equals 5, maybe about here. Okay. Now we know that the function f is always positive, so it can't go down below the x-axis, wherever that is. Maybe it's right there. So what I'm saying is that because of that, and the fact that it's got a vertical asymptote x equals 1, that means that I have to be going up towards that vertical asymptote. So I know that at the very least, the graph of f kind of starts off like this. Now, a horizontal asymptote can definitely be crossed really any number of times, but what's got to happen with a horizontal asymptote is the farther out I go, the closer I got to get to that y value. So that's going to be giving us enough information to solve these two questions, right? Limit as x approaches infinity of f of x. Oh, okay, that's y equals 5 is the horizontal asymptote that we're approaching. That's the idea of the limit as x approaches infinity is the same as the horizontal asymptote. So I'm going to say that's 5. And then the limit as x approaches 1 from the positive side, okay, that's going to positive infinity because of the vertical asymptote, along with the fact that f is always positive. Then now we're going to find the equations of all vertical and horizontal asymptotes. Okay, just to remind you, vertical asymptote caused by divides by 0. Horizontal asymptote, that's we're thinking the limit as x approaches infinity and negative infinity. So maybe I'll do a plus minus there because I forgot. Okay, so for the vertical asymptote, we're going to grab the denominator and say what x value makes this equal to 0. Okay, so I need e to the x minus 1 equals 0. That's the same as looking for places where e to the x is equal to 1. And now you can take the log of both sides if you like, but when you're taking the log of 1, you're asking yourself, what special exponent do I put on e to get 1? So I think this is one we can solve with our eyes. And we're going to say that's x equals 0. Okay. And then for the horizontal asymptote, okay, I'm going to have to be careful because it's got exponential in it. So I'm going to be considering both limits. Limit as x approaches positive infinity. Okay, this is growing really fast. It's going to get huge. And the numerator is going to stay 1, and subtracting 1 isn't going to really make it any less huge. So I know that I've got a huge denominator that's going to go to 0. And then as x goes to negative infinity, e to the x goes to 0. So that's going to go to 1 over 0 minus 1, which is negative 1. And so I'll say that the horizontal asymptotes are y equals 0 and y equals negative 1. Right, and then this next one here. Oh, we're going to do the same thing. So we're going to grab the denominator, and we're going to say, okay, vertical asymptotes caused by division by 0. Where is the denominator equal to 0? Okay, x squared plus 1. Okay, if you aren't already seeing it, that's x squared equals negative 1. You go to take square root of negative 1. You're like, oh, okay, in this class that doesn't happen. It's no solution. So there are no vertical asymptotes. You could say none. DNE, NA, whatever you want to say. Horizontal asymptotes, we're considering the limit as x approaches infinity of 1 over x squared plus 1. And that's going to be 0, okay, right? Because we're thinking bigger on top, bigger on bottom. This is definitely faster growing on bottom. And I think that the same thing will happen as you approach negative infinity. First of all, because there's no exponential in here. But second of all, because you square a number, it's going to remain positive, whether it was positive or negative. So this is always going to go to some huge positive denominator, and it's going to go to 0. So I'm going to say y equals 0 is the only horizontal asymptote of g. I'm going to flip this over. We're going to find the value of the limit. If I try to plug this in, this would go 4 plus 2 is 6 over 0. Okay, so that's bad news. I know that I'm sitting on a vertical asymptote if I have non-zero divided by 0. So I go over here, I kind of draw a little picture. Okay, and since we're approaching 2 from the negative side, I'm going to plug in like 1.9 or something. Okay, and if I think about taking a number that's less than 2 and squaring it, well, it'll be less than 4 because square is kind of like an increasing function. Right? You only get a bigger square by taking a bigger number and squaring it. So I'm thinking 4 minus 1.9 squared, well, that's still going to be a positive number. 5.9 is a positive number, so I've got positive over here. Meaning that the graph of this function is going to be positive while approaching a vertical asymptote. That means it's going to positive infinity. So I would say this came back positive infinity. And then the value of this limit, okay, if I plug in on this, this is going 0 on top, 0 on bottom. So since that's going 0, 0, at this point, all we can do is draw a picture of the graph, okay, or potentially factor and cancel, but there's nothing to be factored on this, right? So we're going to draw a picture. Okay, if it was x minus 8 over the absolute value, or absolute value of x minus 8 over x minus 8, we know it would be 1 up top and negative 1 down below. It seems to me like this one's probably just going to be the opposite. It's going to be negative 1 to the right and positive 1 to the left. Okay, but if you're unsure what you should do, we're approaching 8 from the positive side, we should plug in a number a little bit bigger than 8 just to convince ourselves, like, I don't know, maybe 8.1. And 8 minus 8.1, the absolute value of that would be 0.1. Right? It would become positive. But 8 minus 8.1 itself is a negative number, so I've got negative 1 over here on the right. So I know that this limit is going to come back negative 1. But I can draw the rest of the graph just to remind you what this graph looks like. And the value of the limit. Okay, over here is x approaches infinity. We're thinking about our relative growth rates. And we know that log grows slowest of all. Okay, it grows very slowly, slower than any power of x. And so this is a power of x. So we say this is equal to the limit as x approaches infinity of x to the 1/2 power divided by log x. And since it's growing faster on top, okay, we said it had no horizontal asymptote. Okay, the limit's going to be infinity because both of these things are positive as x is, really big. So this is positive infinity. Okay. And then now this one, as x is approaching negative infinity, the only thing that we can really determine what the behavior is as x approaches infinity is this 1 over x. Okay, and as x approaches negative infinity, 1 over x goes towards 0, right? We're dividing by a huge negative number. 1 divided by a huge negative number is going to be very close to 0. So this is going to be equal to the cosine of 0 minus 3. And maybe you just need to draw yourself a little diagram to remind yourself what cosine of 0 is. We know that 0 is over there. It's the beginning of the unit circle. And we know that cosine is the x-coordinate. So the x-coordinate over here is all the way over. And so we know that cosine of 0 is going to be 1. And so that's 1 minus 3, which is going to be negative 2. All right. And then the last one on the graph of y equals ax minus 3 over x plus b is shown over here. What's a and b? All right, I think I'm going to do b first because that one's just like kind of staring at me. I've got a vertical asymptote here at x equals 1. So I need x plus b to be 0, division by 0 when x is equal to 1. So 1 plus b equals 0. Oh, okay, I see b needs to equal negative 1. Okay. Then I know I'm seeing a horizontal asymptote of y equals 2, so I know that the limit as x approaches infinity of ax minus 3 over x plus b, okay, that's going to be, first degree on top, first degree on bottom. We're just going to divide coefficients. It's going to be a over 1, but that needs to also be equal to 2. So I know that means that a is going to need to be equal to 2. And now, well, that's all for this form. All right, for form J, we're going to start with just a little bit of finding the value of the limit. Okay, and so the first one, as x approaches infinity, we're thinking about our relative growth rates, right? And 4th root of x, that's a power of x, that's x to the 1/4 power. And e to the 4x, that's exponential. And we know in our taxonomy of growth rates, exponential always grows fastest of all. So if it's faster growing on bottom, the denominator's getting big, we're dividing by more, we're getting closer to 0. Okay, so that one was 0. And then over here, as x approaches negative infinity, we have got, okay, a 3rd degree on top, 3rd degree on bottom. Okay, so we're going to be looking at the ratio of the leading coefficients. That's going to be 6 divided by 2. If you want to simplify that to 3, be my guess, but I think actually 6 divided by 2 is a little more clear on how we got that answer. So I'm going to leave it like that. Right. The continuous function f has domain x is greater than 2, and f is always positive. Okay, and the asymptotes to the graph of f are x equals 2 and y equals 3. I'm going to just draw a little picture of the graph. Okay, and this is not the x-axis and the y-axis. This is x equals 2 and y equals 3. Okay. Now, if function f is always positive and it's approaching a vertical asymptote, right, it can't go below the x-axis, and it's approaching a vertical asymptote, that means it has to go to one of the infinities. So I know that in some way, the graph of f has to look like that, right, where it's coming from a vertical asymptote. Now, a horizontal asymptote can be crossed, and, you know, where and how that happens is definitely a very pre-cal level concern that we're not going to really worry about in this class. But we know that a horizontal asymptote means we have to get closer and closer to it as farther we go to the right. So that's also tough. F is as x approaches infinity. It's approaching y equals 3. So I'm just going to fill that in right now. I see that. And then over here, as x approaches 2 from the positive side, well, we got to be going to positive infinity because we're approaching a vertical asymptote and the function is always positive. That's really key there. So that's why it's positive infinity. Okay. Now we're going to be looking at solving for the values of some vertical and horizontal asymptotes, okay? And so just to remind you, the cos of a vertical asymptote is division by 0. Non-zero divided by 0 specifically. And the horizontal asymptote, we're thinking about the limit as x approaches infinity and negative infinity, right? We've got to be careful, especially with one like this that has an exponential in it. The vertical asymptote, we grab the denominator, and we try to solve, okay? If you're like me, you're looking at this and you're thinking this is not likely to be solved, right? Not with real numbers. So we're going to say, all right, e to the x equals -1. And this is where you should, like, if you didn't see it at the beginning, here, you say, okay, e is a number between 2 and 3. A positive number to any power is going to be positive. Even a positive number to a negative power, right? They'll just become small, close to 0. And so this is just not going to be possible. There's no values of x that make that equation true, so there's no vertical asymptote. So I'll just say none. Okay. Now the horizontal asymptote, I'm going to have to be careful. I'm going to say this is the limit as x approaches infinity of 1 over e to the x plus 1. Okay. As x approaches infinity, e to the x also approaches infinity. And 1 stays the same. So I've got the denominator growing really big, numerator staying constant. I'm dividing by more and more and more. That's going to 0. But then I also have to consider the limit as x approaches negative infinity. Okay, as x approaches negative infinity, e to the x goes to 0, right? Because it's like 1 over e to a huge number. We say e to a large negative number. And so this limit is going to 1 over 0 plus 1, which is going to be 1. And so my horizontal asymptotes will be y equals 0 and y equals 1. All right. We're going to do the same thing with this one. We're going to say g of x is 1 over x squared minus 1. And we're going to find the vertical asymptotes by grabbing the denominator and setting it equal to 0 and solving. Okay, x squared equals 1. Okay, we know what's going to make that equal, what I can square and make that equal to 1. That'll be x equals 1 and x equals -1. That was. But then the horizontal asymptotes, that's the limit as x approaches infinity. Okay, -1 like that. And what I'll say about this, similar to what happened on form I, as x approaches infinity or negative infinity, x squared is going to get really big. It's going to be big and positive. So this limit is going to come back 0 to both infinities. And so I say that y equals 0 is the only horizontal asymptote to this graph. So move to the next page. Now we'll find the value of this limit. Okay. When it's just a number, we're going to try to plug in, right? We can't just plug in infinity. That doesn't work. Infinity is not a real number. It can't be plugged in. Okay, but if it's just a regular real number, we're going to try to plug this in. The top is going to go to 6, and the bottom is going to go to 0, which means number divided by 0, we're sitting on a vertical asymptote. It's going to be infinity or negative infinity, because we know it's a one-sided limit. So I'm going to draw a little graph with some vertical asymptote on it. And I'm going to choose a number just a little bit bigger than 2, like 2.1 or something. Okay, so I'll have 6.1 as a positive number divided by, okay, something like 2.1. Well, if I square it, it'll be bigger than 4. If I take a number bigger than 2 and square it, that square will be squared. Okay, so I'm going to say that 4 minus some number bigger than 4 is going to be negative. And if I'm negative while approaching a vertical asymptote, well, then that limit has to be negative infinity. So I would say that's going to be my answer down there, negative infinity. And then over here, okay, if I was to just plug in on this one, I'd see that this is going 0, 0. And at this point, when we see 0 and 0, we have to draw a picture of the graph. Right? And so what I'd say is if this was absolute value of x minus 8 over x minus 8, we know this would be 1 up here, negative 1 down there, draw the picture and move on. But it's a little different, right? You would, I think the natural thing to think would be, like it would flip, right? And that's what's going to happen. But what was I thinking? Oh, best to be sure, right? So let's pick a number that's a little bit less than 8, like, I don't know, 7.5. That would be a half. That would also be a half, both positive. So I know it's going to be 1 as I approach from below. And, you know, I can complete the graph down here. But as I'm approaching 8 from the left, y is staying pretty steady at positive 1. So I'm going to say that it's equal to 1. Okay, the value of the limit here. Okay, as x approaches infinity, we're thinking about relative growth rates, which is growing faster, which is growing slower. And so, okay, remember this is a power of x, this is x to the 1/2, and log grows slowest of all of them. So if you're growing slower in the the denominator than you are in the numerator, your quotient is getting bigger and bigger and bigger. These are both positive numbers when x is a large positive number. So I'm going to say that this limit comes back positive infinity because it's faster growing on top. Okay. And now as x approaches infinity, 3 is going to remain 3. Cosine, we don't really have anything for that, but 1 over x, we know what's going to happen with that. So I might say, all right, as x approaches infinity, this fraction on the inside of the parentheses, that's going to 0. So this is going to equal 3 minus the cosine of 0, which, okay, if you need to be reminded, we're going to go over here, we're going to draw a unit circle. We're going to go over here to theta equals 0. Because we're trying to take cosine of 0, and cosine is the x coordinate, so okay, that's going to be all the way over to the right. That's going to be positive 1. So 3 minus 1, which I know that you know is 2. Okay. Now the last question for this quiz is, okay, here we've got a picture of a graph that's got some kind of apparent vertical asymptote and some kind of apparent horizontal asymptote. And then what was I thinking? Oh, okay, so I'm going to start with vertical asymptote. Okay, the vertical asymptote is x equals negative 2. And that needs to cause me to be dividing by 0 when x is negative 2 seconds. All right, and so that means that negative 2 plus b needs to equal 0. I'm seeing that being b equals positive 2. And then for the horizontal asymptote, it looks like, okay, the limit as x approaches infinity, or negative infinity, it's got to be equal to negative 1. So as x approaches infinity, ax plus 1 over x plus 2, plug in on b, doesn't really matter. Okay, because first degree on top, first degree on bottom, I'm going to divide the coefficients. That limit's going to be equal to a over 1. But I also know that that limit needs to equal negative 1 because of the equation of the horizontal asymptote. So I know that means that a is negative 1. Okay. And well, that's all for this quiz. All right, now we're going to move on to continuity, quiz 1.3, Form I. All right, so the first one is talking about let f be this function that's already factored for us. At what values of x, if any, does f have a removable discontinuity? A removable discontinuity is one that's a hole in the graph. We get that by canceling on top and bottom. we see 0 over 0 in the original form of the equation. So I'd be canceling off 1 power of x plus 2, so I know that x equals 2 is the removable discontinuity. That's all I gotta say. Okay, at what values of x, if any, does G have a non-removable discontinuity? Well, it's probably not going to be 4, right? I bet that x minus 4 is a factor of this, and it'll be the other factor that's going to give us the non-removable, because non-removable in this situation is going to be a vertical asymptote. Okay. So this is x minus 4 over x plus 5 times x minus 4. Okay. We can cancel these off, so we know there's going to be a hole in the graph at x equals 4, but otherwise it'll look like the graph of 1 over x plus 5. Okay, that's 1 over 0 when x is equal to negative 5, so I'm going to say that's x equals negative 5 for the non-removable. Okay, now we've got something pretty similar, and we're going to say h is discontinuous, but the limit exists. This is code for removable discontinuity. So it's very similar to question number 1, right? Okay, I'm just going to say, all right, I'm going to factor this. That's x times x plus 6. And 12, okay, that would be positive 6, negative 2. And, okay, so I'm going to cancel stuff off. The removable discontinuity is where I canceled, right, where the hole in the graph is, and that's going to be x equals negative 6. And then, all right, over here, this discontinuous, but the limit does not exist, that's non-removable. Okay, we're not going to be having a jump in the graph because so we're just looking for the vertical asymptotes. So the numerator can be factored with x plus 2 and x minus 2. And then what is this? Oh, it'll be plus 3 minus 2. So x plus 3, x minus 2. Okay. And so the non-removable discontinuity won't be where I canceled. It'll be where I get number divided by 0. And so that would be at x equals negative 3. Okay. I'll go back. Right. Okay, f is continuous at all values of x. Means it's got to be continuous at x equals negative 1. So I need x plus 2 to be equal to ax plus b at x equals negative 1. So I plug that in and I get 1 equals negative a plus b. And then I need also ax plus b to equal x squared plus 9. At the point where x equals positive 2. Okay, so I will go in and I'll plug in x equals 2, and I'll get, I'm going to go over here so they look the same. So 4 plus 9 is 13 equals 2a plus b. Now I'm going to solve this system, right? I think maybe I'll double this equation. I mean, at this point you can use substitution, elimination, however you want to solve it. Just trying numbers. Okay. But I'm going to double this equation so I can do elimination. So if I double, I'll have 2 equals negative 2a plus 2b. And then I'll get 15 when I add these together equaling 3b. So I know b has to equal 5. Negative a plus b equals 1. I think that would need to be a equals 4. Yeah. Okay, so a equals 4, b equals 5. Then, okay, this problem. Now this one wasn't scored for this year. Okay, who knows, maybe in the future year it is. But this is something that we're going to do later on in the course where we have to cook up a new function. Okay, if we want to say, okay, basically the idea is w of 0 equals 3,000 divided by 10 is 300. And then w of 8, no, pardon me, I was like, that doesn't make any sense. Okay, w of 0 is 3,000 divided by 2, which is 1,500. That's more like it. W of 8, that's equal to 3,000 divided by 10, which is 300. So since it goes from bigger than r to smaller than r, and they're both continuous, they are going to have to intersect. I drew a picture of this in class. But I'm going to, I can't apply the intermediate value theorem to two different functions, right? What I need is to get a new function, and so I will let f of t equal w of t minus r of t. Okay, I'll say that because w and r are both continuous functions for 0 to 8, that means that f is continuous on the interval 0 to 8. Okay. As a result, well, actually, I'm going to say f of 0 is equal to, okay, w at 0, 1500 minus 1340, which is a positive number. F of 8 is going to equal 300 minus 700, which is a negative number. So since f is continuous and it went from positive to negative, I know f equals 0 for some t between 0 and 8. Okay. And that's going to be the reason why. Okay. That'll be all. Okay. So let's move on to Form J. Right? But you don't like that whole thing about applying the intermediate value theorem to a difference of two functions. That's not something you need to worry about at this point in the course, but it's something that we're going to do eventually, you know, as we get our skills stronger. So, okay, Form J. And at what values of x, if any, does f have a non-removable discontinuity? Okay, non-removable discontinuity, that is not a hole in the graph. That's a vertical asymptote. So if I was to cancel stuff off, I'd lose that. Okay, and the hole in the graph would be at x equals 2. Okay, the non-removable discontinuity is going to be x equals 1 because that's going to cause, you know, non-zero divided by 0. That's vertical asymptote. That's non-removable. All right, so x equals 1 there. Number 2, x minus 4 over x squared plus x minus 20. Let's factor that first. Okay. Okay, the bottom is going to be x plus 5 times x minus 4. And so I can cancel these. And remember, a removable discontinuity is a hole in the graph. And we get a hole from canceling, so that's happening at x equals 4. Okay, discontinuous, h is discontinuous, but the limit of h exists. Oh, whoops, I didn't even notice this typo here. Nobody pointed that out to me. But yeah, that should be f of x. Okay, and it's probably that way on the other version of the quiz too. But I'm going to say, all right, this is just code for removable discontinuity. Right? Removable is hole in the graph. Hole in the graph is where the limit exists, but it might not be equal to the value of the function. If it's discontinuous, then it must not be equal. So I'm going to start by factoring. Okay. And canceling. Okay, I canceled x minus 2 over x minus 2, so that's going to tell me the location of the hole, and the location of that hole is going to be x equals 2. Down here, discontinuous and the limit non-existing, that's non-removable. Okay. So we're going to say, all right, well, we need to factor. And bottom is plus 6 times x minus 2. Okay. And so non-removable, I cancel off with there, and okay, well, the non-removable discontinuity is going to be here, and that's going to be where we get a vertical asymptote. After canceling, I'm still dividing by 0, and that's going to be x equals 2 again. Okay, so that's it for the front side. All right, and then the last problem that we did, number 5, is f is continuous at all values of x, and we need to figure out what a squared plus b squared is. I made the mistake on the previous form. I didn't take this all the way. Yep, I said a equals 4, b equals 5. You'd have gotten 0.8. You got 0.8 if you did this, right? You didn't read the instructions as closely as you could have. A squared plus b squared is 16 plus 25 equals 41. That's what I was supposed to do there. Whoops. Oh well. Can't take it back now. Okay. You know, I'm always good for an error too. So I need these two things to be equal at the x value they share. So I need x plus 4 equals ax plus b. at x equals -1. But then I also need x squared plus x to equal a, this time at x equals 2, the point that they share. Okay, you can see that. And so I'm going to plug in x equals -1, so that would be 3 equals -a plus b. And over here, I have x equals 2, that's going to be 4 and 2 is 6 equals 2a plus b. And now I'm going to, hold on. Oh, yeah, pardon me, I was looking at this one. I'm going to double this equation to set up for elimination. If you want to do substitution, be my guest. Do it your own way. Okay, but I'm going to double, and I'll get 6 equals -2a plus 2b. And then I'll add it together, and I'll get 12 equals 0 a's and 3 b's. So b feels like 4. And then -a plus b equals 3. So -a plus 4 equals 3. If I subtract, I get -a equals -1, a equals 1. So I won't forget this time. A squared plus b squared is going to be 16, and 1 is going to be 17. Okay, for number 6, if you're interested in the solution to that, we didn't grade this one. Okay, so if you tried it, it wasn't counted against you. I graded most of these, and I didn't have time to read your response and give you feedback on it. But if you want to know how to solve this problem, you need to go back a few minutes in the video, because it was the exact same on Form I, and I worked it all the way through with details. So just skip back a few minutes, you'll see it. Got a lot of writing. But now I think it's time to move on to quiz 1.4. Yeah, the most recent one. Okay, so you might have taken this one today or on Friday or something as you're studying for the for the test. First question here, we've got a piecewise defined function. Is it continuous at x equals 3? Justify my answer. Okay, you might not have justified it the same way I did, and that's okay. We're not strict on our justifications yet. We will be eventually. But for now, what we're interested in is the limit as x approaches 3 from below. That's going to be 3 times 3 minus 2, which is equal to 7. Then I'm going to consider the limit as x approaches 3 from above. Okay, I'm going to get that from where x is bigger than or equal to 3. X plus 4, that's 3 plus 4. That's also equal to 7. Since the limit from the left is equal to the limit from the right is equal to the limit of the function, okay, because it's 3 plus 4, I'm going to say yes, it's continuous. Okay. But is g differentiable at x equals 3? That remains to be seen. Okay, no, I don't think so. Because before x equals 3, it's got a slope of 3, right? So that's pretty steep, right? And we determined that it was continuous, so it could be differentiable, provided that these two pieces of graph met up smoothly. But I'm going suddenly from having a slope of 3 to having a slope of 1, and I know that's going to give me a sharp corner. So I could just say no sharp corner. We don't really have the tools yet to properly justify our answer. Now we're going to let h of x equal the absolute value of x minus 2. And I might just draw a picture of the graph of that. Okay, it makes a v, right? So h prime of 1 is the slope at a point like here. The slope of this is going to be negative 1, pardon me. We know that absolute value of x is equal to x when x is positive and negative x when x is negative. We know that the slopes of these things are 1, I guess, from our experience with that function. Okay, so h prime of 1 is negative 1. H prime of 2 is not going to exist because of the sharp corner. And then h prime of 3 over here, well, that's a positive slope. That's going to be positive 1. Okay. And I think that when we're grading this, we're going to give credit for negative, positive d&e. Okay. Because some people didn't know that they were supposed to know that the slope of this was negative 1 and 1, or just didn't know, and I'm realizing I don't necessarily expect you to. After today, or after you get this quiz back, I do expect you to know. So f prime of 3 on this next one, where we're getting a picture of the graph and a picture of the tangent line, well, f prime of 3 is the slope of the tangent line at x equals 3. Okay, well, I've got the tangent line. I can find the slope by doing a little rise over run. Okay, it ran 1, it rose negative 2. That's going to be negative 2 because it's the slope of that line. at what values of x, if any, is f prime of x equal to 0? Where is the slope of the tangent line equal to 0? Let's say it's right here. Okay, and that looks like x equals 2. And then if the next question is if f of 0 is equal to 0.8, what's the average rate of change of f on the interval 0 to 3? Well, that's going to be the slope of that line that I just drew in. But we're better off just using the formula, right? That's going to be f of 3 minus f of 0 divided by 3 minus 0. And so I'm just going to plug in f of 3 is 2, f of 0 is 0.8, divided by 3 minus 0, and that's going to be a safe place for us to stop, right? You could call that's 1.2 divided by 3, which I think is probably the same as 0.4. We don't need that, right? We're good here. Now, if you simplified it to 0.4, good for you. You know, you're good at arithmetic. But you're no more right than somebody who would just stop there. Okay. Number 7, another average rate of change question. Find the average rate of change of h on the closed interval 4 to 8. So that's going to be h of 8 minus h of 4 divided by 8 minus 4. And that'll be equal to, okay, 2.5 minus 4.5 divided by 8 minus 4. Okay. We could say, okay, wait, that's negative 2 divided by 4. That's negative 1/2. Okay, but this is a safe place to stop, and I would encourage you to stop here, right? Showing you that if you pardon me. Forgot I was still rolling. I was responding to an email between questions. Okay, not a big deal. Hopefully that wasn't, I don't think that went very long. That was a quick 3-word response, so I really hope that was quick. Okay, at what values of x is that limit of rise over run as run goes towards 0 greater than 0? Okay, so I'm going to translate this to something we're more familiar with. Where is the slope positive? Okay, well, the slope at A is going to be undefined because of the sharp corner. Slope at B is going to be undefined because of the discontinuity. Slope C is going to be 0, because we're right here at the bottom, flat tangent. Slope at D is going to be undefined as well because of the discontinuity, so I'm left with just E. Okay, and then at what values of x is f continuous but not differentiable? Okay, that's going to be x equals A. Okay, that's like a sharp corner and a vertical tangent are the ones that are continuous but not differentiable. Okay, I don't see a vertical tangent. Vertical tangents are kind of hard to see. You kind of have to be told that it's there. But this sharp corner we can definitely see. So x equals A. It's continuous. I could draw it in one go through A, but it's too sharp to be differentiable. We can't get one slope there. Okay. Then the question is f differentiable at x equals b? Give a reason for my answer. Okay, well, I already kind of said it, but no, because it's discontinuous. Okay. Okay, and that's going to be the reason for my answer, is the discontinuity. If you were talking about, there's no place to put a tangent line in, I get it. We probably credited you when we graded it, but that's going to be the best response there. All right, now let's work form J. So here they're giving us a piecewise function, and they're going to start us off asking, is g continuous at x equals 2? Just one answer. Okay, so we need, the definition of continuity is the limit of the function equals the value of the function. So I might start with the value of g of 2. Okay, so equals 2, and that's equal to 2 times 2 plus 1, which is equal to 5. And then the limit as x approaches 2 from below, we'll start with that, of g, is going to be, I'm going to go over here where x is less than 2 and use that formula. Whoops, 4 times 2, 2 times 4, same thing, right? 8 minus 3 is 5, and then the limit as x approaches 2 from the positive side of g is going to be, I use this formula and plug in 2. But we already know what's going to happen because we used that formula already the once. And since these are all three the same, right, the limit is equal to 5 because both of these are 5. The limit equals the value of the function, so yes, that's the justification. Now, you may have used some words or something like that, and that's completely fine, right? You might not be totally here yet with your justifications. You'll get there eventually. That's not the focus right now. For now, I need you to be thinking about the concepts, working the problems, worry about the justifications a different day. All right. So the next question is g differentiable at x equals 2? And just find my answer. Okay. Well, I'm going to say no because, okay, it starts off and it has a slope of 4 before x equals 2, and 4 is very steep. And then afterwards, it's got a slope of 2, which is still pretty steep, but not as steep, and that's going to cause me to have a sharp corner, right? So I'm going to say no because of the sharp corner. Okay. The absolute value of x minus 3 looks like that. Okay. And so h prime of 3, that's a sharp corner, that's going to D&E. Okay. H prime of 4 over here, that's positive 1, but if you said positive, we're going to give you the credit for it on the quiz. You should be credited. That's kind of just a trivia fact from, I guess, Algebra 2, is that the graph of y equals absolute value x has slopes -1 and +1. Because it's like y equals x and -x. But over here at x equals 2, that's where the slope is going to be -1. Okay, but if you said negative, that's right? We'll get there with time. All right. Now here's the graph of y equals f of x along with the line tangent to the graph of f at x equals 1. And they're going to ask us what's f prime of 1. Well, f prime of 1, that means the slope of the tangent to f at x equals 1. So I will say, all right, that's got a slope of 2. And hold on a second. I had to respond to another email. I should not have the email like behind my recording window, right? I shouldn't be able to see it coming in, but I've got it set up today, so I'm almost done, right? So give an example of a value of a value of x where f prime is 0. Okay, I think that's going to only be this one. I'm looking for a flat tangent, that's going to be x equals 2. Okay, and then if f of 4 equals 0.8, find the average rate of change of f over the interval 1 to 4. Okay, well, that's going to be f of 4 minus f of 1 over 4 minus 1, which is going to be, all right, well, f of 4, we're saying that's 0.8. F of 1 is... Oh, I was like, how am I supposed to know? I was looking here. X equals 1, y equals 2. So that's going to be 0.8 minus 2 divided by 4 minus 1. And this is a safe place to stop, right? So... on to the back, another average rate of change question. We love these, right? Because we know it's h of 8 minus h of 0 divided by 8 minus 0. We're just going to plug in these numbers from the table. What could be better? So that's 2.5 minus 3 over 8. Done, right? You can simplify that. I think that's -1 over 16, but don't, right? Just stop there. Okay, now we've got this graph, and we're going to answer some questions about it. Okay, we're asking what x values is the limit, the limit of rise of a run as run goes towards 0 equal to 0. Okay, so we're thinking that's just code for the slope of the tangent line. F prime of x equals 0. Okay, where is f prime of x equal to 0? Oh, that's down here. I just completely misread this question, assuming it was the same as form I. Okay, a value of x where f prime is negative is not going to be here. F prime equals 0 there. This is not a valid answer. I outsmarted myself. So I'd say here at x equals 3 is a place where f prime is negative. Really, any place beyond x equals 2 would work for this problem. Okay, so that when they ask where f prime equaled 0, I'm seeing that's x equals c. I knew I wouldn't ask that same question twice on the same quiz. Okay, and then I'll say, okay, what values of x is f continuous but not differentiable? Okay, continuous but not differentiable, that's either going to be a sharp corner or a vertical tangent. I don't see anything even near a vertical tangent, so it's got to be that sharp corner here at x equals. And then the last question is f differentiable at x equals b? You give a reason for your answer. Okay, well, at x equals b, the function's discontinuous. And we know that differentiable gives continuous. And we also know that not continuous automatically gives not differentiable. So I'm going to say no, it's not differentiable at x equals b. I mean, there's nowhere to even put a tangent line, right? I'd say no because f is discontinuous at x equals b. Okay, and that is all of the quizzes, or at least all of the Form I and Form J quizzes for Unit 1. Thanks for watching. Hope this helped.